对。
In this presentation, we will first give you a brief introduction talking about the email these days. Then, we will introduce and compare some widely used email encryption methods, mainly focusing on the end-to-end email encryption. After that, a detailed analysis will be given in the perspective of an attack of these approaches. Finally, we will conclude the presentation. Email is one of the most commonly used communication technologies in today's life, which is a method of exchanging messages between people using electronic devices. Current email system is based on a store and forward model, which only supports ASCII character sets, which is then enhanced by MIME, so that more character sets and medias can be carried. MIME, which is the abbreviation for Multi-Purpose Internet Mail Extensions, enables users to write emails in character sets other than ASCII. It also supports non-text attachments, such as video, images, and application programs. Even though MIME is designed for SMTP, it is also important in other communication protocols, such as HTTP. There are two main approaches to encrypt email. The first one is on the transport level, and the most powerful and prevalent implementation of it is called Transport Layer Security, TLS, and its deprecated predecessor, Secure Sockets Layer, SSL. Another approach of email encryption is end-to-end encryption, and the best two implementations are called SMIME and PGP. Secure Multi-Purpose Internet Mail Extensions, which is also known as SMIME, is an extension of the MIME. It is proposed to make sure the email can be sent securely. It is built on cryptography message syntax, which defines 6 content types. The SMIME provides the following functionalities: authentication, message integrity, non-repudiation of the origin, and the encryption. For encryption, Cipher Blockchain (CBC) is chosen to be the operation mode. Moreover, SMIME is now built into the majority of modern email software and interoperates between them.
PGP stands for Pretty Good Privacy. We will explain two modes of service of PGP. The first figure illustrates the digital signature services provided by PGP. The EP and DP mean public encryption and decryption. The Z represents zip function to provide compression features. The whole process works similar to the message authentication code. The second figure explains another service provided by PGP, that is the confidentiality service. Firstly, the sender will generate a one-time random key, which works as a symmetric key to encrypt the compressed messages. After that, he will use the recipient's public key to encrypt the symmetric key and send it along with the encrypted messages to the recipient. For the recipient, the process of decryption is just the other way around. These two kinds of services can be combined to provide a more secure mode with both the digital signature and the confidentiality. The most significant feature of PGP is its decentralized trust model, or PGP called Web of Trust. Unlike the traditional trust model mentioned in the public key infrastructure, where the trust is established through a process of registration and issuance of certificates at and by the certificate authority, the Web of Trust model provides high freedom, allowing everyone progressively accumulate and distribute their key to the people that are considered as reliable by their trusted introducers, eventually causing the emergence of a decentralized fault-tolerant web of confidence for all public key. As we have discussed the features of SMIME and PGP independently in the slides above, we will compare their differences in 6 perspectives, including message encoding format, public key certificate and distribution, symmetric key encryption algorithm, digital signature algorithms, and message compression. Both of them use RSA SHA-256 digital signature algorithms, and they have minor differences concerning the message encoding format. The most significant difference is the trust model. The SMIME uses the X509 PKI while the OpenPGP uses the Web of Trust. They use different modes of operation described in the symmetric encryption algorithm. For SMIME, it is the cipher block chaining, while for OpenPGP, it is the cipher feedback, which we will explain in detail in the following sections. Another feature of OpenPGP is its support of message compression.
It seems that these two end-to-end email encryption protocols are secure and well-defined. However, researchers in 2018 designed an attack which can reveal the content of encrypted email, called eFile. First, let me introduce the malleability gadget attack on SMIME. From previous slides, we know that SMIME uses CBC mode for encryption and decryption. One ciphertext block C1 first decrypt, then XOR previous ciphertext block C0 to get the plaintext block P0. XOR is a malleable operation, which means that one single bit error in one of these two operands of XOR results in one bit flip of the final plaintext at the same position. In this case, we can modify the C0 to affect the decrypted content P0. The CBC gadget is designed based on the XOR operation. We can get 0 if XOR the known plaintext P0 itself, and then XOR another plaintext PC that we want email client to process. Meanwhile, we also introduce one block random sequence bits in P0 if we modify C1. As for the practical attack, here is an example. The original text is these 4 blocks. We can use CBC gadget to introduce the read content and construct the attack payload. The image tag is a backchannel that can be used to do interaction with network. The block modification includes changing, duplicating, and reordering. Then the request is constructed and then sent to the HTTP server. Besides, the direct exfiltration attack induces the email client to send the decrypted content to this HTTP server.
Similar to SMIME, malleability gadget can also be used to attack OpenPGP, although there are 2 more obstacles need to be considered. OpenPGP uses modification detection code to check the integrity of the message. If the message is modified, then the email client will find out. However, the OpenPGP standard is ambiguous and does not specify that the email client must not display the message to the user, so MDC warnings can simply be ignored, or the email client can even strip the implementation of MDC. Another obstacle is that OpenPGP compresses data by default using the deflate algorithm, which is based on Huffman coding and LV77. Unlike SMIME, since the plaintext is compressed, so it is usually more difficult to guess. This is a simplified figure shows how to use a compression structure to create an exfiltration channel. Using the malleability gadget, the attacker can create 3 ciphertext blocks, which can be decrypted into useful text fragments. These fragments are a valid OpenPGP structure and contain exfiltration channel. Then the attacker can create a segment containing backreferences, then concatenate and order the ciphertext blocks so that they can be decrypted into 3 text fragments, along with the target plaintext block. Once the victim decrypts and decompresses the email, the final text will result in a concatenation of text fragments and a compressed segment. Finally, the compressed data is linked to the server that the attacker had.
How to ensure the security of end-to-end encryption? First, we need a strong email encryption algorithm like RSA or triple DES to resist the cryptanalysis. Second, strong protocol design is also significant. Like SMIME, it should use signed-then-encrypted scheme to deliver email. And both for SMIME and OpenPGP, they need to detect the modification of the original email. Besides, the published standard should state the countermeasures when email client detecting changes. Last but not least, strict compliance with standard ensure the effectiveness of security. Anomaly detection should be reported to user every time, and it also should restrict the interaction between client and server to prevent the direct exfiltration attack.
First, we briefly introduced the email and discussed the 2 main E2E email encryption protocols, SMIME and PGP. We also compared the differences between them and find the potential vulnerabilities of the 2 protocols. Last but not least, We analyzed the cryptographic schemes of the two protocols and put forward some mitigations to enhance the safety of them.